On the other hand, with a practically continuous current, the arc is easily maintained, the column being constantly kept at a high temperature and low resistance. The higher the frequency, the smaller the time interval during which the arc may cool and increase considerably in resistance. With a frequency of 10,000 per second or more in any arc of equal size, excessively small variations of temperature are superimposed upon a steady temperature, like ripples on the surface of a deep sea. The heating effect is practically continuous, and the arc behaves like one produced by a continuous current, with the exception, however, that it may not be quite as easily started, and that the electrodes are equally consumed, though the writer has observed some irregularities in this respect. The second cause alluded to, which possibly may not be present, is due to the tendency of a machine of such high frequency TD maintain a practically constant current. When the arc is lengthened, the electromotive force rises in proportion and the arc appears to be more persistent. Such a machine is eminently adapted to maintain a constant current, but it is very unfit for a constant potential. As a matter of fact, in certain types of such machines a nearly constant current is an almost unavoidable result, as the number of poles or polar projections is greatly increased. The clearance becomes of great importance. One has really to do with a great number of very small machines. Then there is the impedance in the armature, enormously augmented by the high frequency. Then, again, the magnetic leakage is facilitated. If there are 300 or 400 alternate poles, the leakage is so great that it is virtually the same as connecting in a two-pole machine the poles by a piece of iron. This disadvantage, it is true, may be obviated more or less by using a field throughout of the same polarity. But then one encounters difficulties of a different nature. All these things tend to maintain a constant current in the armature circuit.